Right. So, so far as so I understand that already. So now my this screen is shared, isn't?
Yes, sir. It is shared. Yes, full screen is there.
Yeah, yeah. So I will do that. Just a minute. Resolve. Screen is getting shared, so I'll start with the topic. Okay. So you were already in already the discussion on band, and also on the uh, carrier concentrations, how carrier concentration is obtained in a given, I mean, for example, in conduction band, what is the value of carrier concentration based on Maxwell-Boltzmann distribution? I think these topics were discussed, isn't? Otherwise, you can. So you just tell me.
No, sir, it was not covered in so deep. So
Uh,
I have just these energy band diagrams only surface level I have covered in the morning session. Just the
oh,
categorization
okay,
of
okay.
different materials, how the just the shifting of this Fermi level band and all these things. Just I have discussed, but no formula or related things I have not discussed in detail. I have not
Okay,
discussed.
okay. And in different materials or the different at different junctions, why the Fermi level is invariant? Was that
The,
discussed or
no, no, sir. We have not gone to the junctions. Junctions we will start tomorrow, sir.
no, no, not junctions.
Ha.
Fermi level is invariant in equilibrium. Was that
Yes, sir.
discussed?
No, 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 sir. We have
Okay,
not
okay. So
covered.
I'll start from that point then. So
Okay, sir.
whatever keep discussing, if that topic has been covered, you please tell me. I will not do that, and then I'll do the something uh, after to be done after that. Isn't like that?
Sure, sure, sir. Sure.
Okay. So okay. So I will start discussing from the idea that Fermi level is invariant uh, in different materials. Okay, whenever there is whenever there is uh, this a thermal equilibrium. Okay, give me a moment.
Sir, your voice is not audible, sir.
No, no, I'll just begin. Just give me a
Okay.
moment because we are doing in a more discussion manner, isn't? So I'm also taking a while.
Okay.
Uh, just give me a moment. Just give me a moment. I'll let's see. Oh, you're not. It's not that. It's okay. I'll just explain this way. Okay. So, you have got introduced to the idea of Fermi levelism. And have you seen Maxwell-Boltzmann distribution and Fermi direct distribution?
No, sir. Just I told that there are three bands: conduction band, Fermi, and the valence band, and told that the Fermi level is 50% probability. I have not discussed any kind of equation because I just started from the scratch, so I
Okay, I
couldn't.
understand. I
Yes,
understand. I understand.
yes, sir.
So it is okay. So we need to introduce Fermi direct distribution and Maxwell-Boltzmann distribution, isn't it? So
Yes, sir.
then we can go ahead. Okay.
Yes.
So uh, let us begin with let us begin with uh, Fermi direct distribution or bands. Why these energy bands are there? So very briefly. So very briefly, why the energy bands would be there. So see, all the atoms, if we speak very intuitively, all the lattice atoms are now very close to each other. And when they are very close to each other, their uh, individual, if they were ideally separated atoms, their individual electron energy bands would be uh, separate, isn't? So now, when they are all coming very close to each other, the valence electrons are as if shared. And if the valence electrons are shared, their energy. So now, from Pauli's looking at Pauli's exclusion principle, no two electrons would have the same quantum state, isn't? Each of them would have a different state. So therefore, all the electrons would have a different. So no, not more than two electrons would be occupying. So no two electrons would have the same quantum state, isn't? So so when they come close, you can very at a very in a very rough manner, what we can assume is that all their energy levels they come close to each other and they form a band. That's what I think was told to you in the morning. So if they form a band, now what is the way this what is the way they would uh, so if they now form a band, how would the carrier concentrations behave? So that so we can say, let us say that these form a band. So EK diagram, etc. I'll not get into, but I think that might have been discussed in the morning. Was it discussed EK diagram? But I'll not. If it was not, it's okay. I'll not get into that. So what we can say is that now there are two bands. Suppose so one is the valence band and the another one is conduction band, suppose. Okay, so now there are the valence band has all the valence electrons in their original. You can think of it intuitively as if all the valence electrons are in their original energy state. Okay, so they are quite tightly bound with the lattice atoms. So they and there so they are all the electrons are here like this, and so you can assume that this is all energy, isn't electron energy. So it is, if you look at the positive energy, then it is this is actually electron energy. So it increases uh, in so when the electron energy increases, the conventional energy actually decreases. Okay, so you can think of it that way. So if the electron energy increases, the electron is less tightly bound with the lattice atoms. If the electron is tightly bound with the lattice atoms, then what it means is that it's an electron's energy is low, or the energy state of the entire system is low. If the energy is higher, the electron will have more propensity to move out of the lattice atom or nucleus sphere of influence. Okay, so you can think of it that way. So that's therefore in the valence band, the electron energy is now smaller. So if you give it more energy because of the quantum properties or quantum states not being available here, no, none of the electron energies are available here. So the electron has to be given an energy which is equal to the band gap, Eg, so that it gets excited here. Okay. Otherwise, it cannot move. So an energy equivalent to Eg must be given to the valence band electron, so that it moves to the conduction band. And now, where is this electron which moves to the conduction band? It is, suppose it is at the highest possible energy level of the valence band, and there it would have the maximum probability to move to the conduction band, isn't it? So see, with the, suppose it is moving to the conduction band through thermal energy. Okay, so thermal energy is a statistical property, isn't it? So it is so thermal energy is how much how much energy each of the electrons here would have, and it would depend on that. So it's on an average. So it's a so the most probable electron to move to the conduction band would be at the edge of the valence band. That is at the top edge of the valence band. Now, what is this distribution like? So, so you have, suppose you have benches in the in a classroom like this. So you have benches like this in a classroom, and students enter. Suppose you have a class in which there are 40 benches like this, and only 5 students are there. Then they can occupy, and each of these benches can have 2 students sitting on them. Okay, like that. These are 2 student occupancy benches. So in that case, if there are 5 students who enter the class, they can sit anywhere, no problem, isn't? So that is so likewise, if the valence, if the conduction band is empty and only a few electrons are to occupy the conduction band, there are a lot of energy states available here, all the energy states above this. So this is like x-axis. Okay, this is energy axis. Okay, so electron energy axis. So now they have all the energy states available to the electrons. So it's as if 5 students are entering this class with classroom with 40 benches, each having 2 seats. Okay. So, and here, so there are all energy states in the conduction band. Each energy state can be occupied by 2 electrons, so to say, because from Pauli's exclusion principle, you can say that only 2 electrons can occupy an energy state in this system. Okay. So now, so if that is the case, statistics, how would you solve the statistics? Then um, each of the energy state is now freely available. So this constraint that an energy state cannot be occupied by more than 2 electrons has no meaning. So if the available energy states are very large compared to the electrons, Pauli's exclusion principle is superfluous. It doesn't apply. It is valid, but it is not. It is not important. Okay, it's as if there are 40 benches with two occupancy and there are only 5 students. They can sit freely anywhere. It this constraint that the bench has only two occupancy has little impact. Okay, or has no impact. That's what we should write. Has no impact. Okay, but if in case, so this leads to what is known as Maxwell-Boltzmann distribution in a layman language. If you use some statistics, then you get Maxwell-Boltzmann distribution as the answer for this. Okay, we'll discuss that further. Now let us look at another scenario where of the 40 benches, 30 are already occupied. So that is, you already have 60 students. And now 5 students enter the class. Or of the 40 benches, some 34 benches are already occupied. Or 30, suppose of the 40 benches, some 32 students benches are already occupied. So 8 benches are left. And 5 students enter. Now, when they randomly distribute amongst the 8 empty benches, the constraint that there are each bench can take only 2 students will have a huge impact on the distribution. Am I right? So if the available free energy states are few. So these are all layman kind of language. This is all layman kind of language, not a formal way of looking at things. But we want to develop an intuitive understanding. That's why we are doing this. If the available energy states are few compared to electrons, so what it means is then Pauli's exclusion principle has an impact on the distribution. Okay, so this kind of a distribution is called Fermi direct distribution. So these distributions are derived in a way similar to the way um, we do in say 11th 12th standard. So it is like you have n number of uh, n number of say boxes, and you want to fill them with balls. Each box has an occupancy of two balls. How would they get distributed if there are 100 boxes and 10 balls coming, if there are 100 boxes and 90 balls coming, like that. So those problems, the way you solve, um, the same way these distributions are solved and derived. This distribution formulae, I will be giving them directly, but they are derived in the same way. It's the same kind of arguments. Only thing is that you are now not with 100 boxes and 90 electrons, 90 balls, but you are dealing with some 10 to the power 20 boxes and 10 to the power 12 balls, like that. So it would you are dealing with very large numbers, and that is how this distribution formulae come. But otherwise, the way they are solved or the way they are derived, this distribution formulae is just like the way we did it in the case where you needed to find out the distribution, the probability, the probability of the balls being distributed or would depend when there are certain number of empty boxes and certain number of balls to be distributed within those empty boxes. Okay. So this what is this Fermi direct distribution? So now these electrons are here in at 0 Kelvin. What would be the nature of the electron? Suppose you are not dealing with semiconductor. So this is say silicon, but you are not dealing with semiconductor. You are dealing with a metal. Suppose. Okay. So and it's always like this. Suppose you are dealing with a metal. So in metal, there are these two. You will not find these two bands and all that. It's all a continuous band of energy states. Okay. So in that, what is the distribution? So you find that at 0 Kelvin, the electrons are all within a certain, below a certain energy level. Okay. So all the electrons are below a certain energy level at 0 Kelvin. So the electrons have no energy in that sense. I mean, they are bound tightly with and they have um, no ambient energy coming from the ambient environment. Yeah. So they are all below the so-called Fermi level. Okay. Once there is, or you can also plot it this way.
Sir, I'm sorry to
Yeah.
disturb you. Your presentation is not visible to us. Maybe you need to present it again.
Okay. So was it visible earlier?
Ah, yes, it was visible. Just now it is not visible, sir.
Okay. So maybe I need to share it again.
Yes,
It
sir.
somehow got hung and therefore I had to
Yes, sir.
redo it. So I think I need to reshare it. Now is it visible?
Yes, sir. Now it is visible, sir.
Actually, you
Yes.
tell me if you have already covered the topics that I'm discussing.
Sure, sir. I have not covered these topics. So
Yeah.
you are going right, sir. Yes, sir.
Yeah. So tell me whenever I need to stop. Okay.
Yes, sir. Yes.
Yes. So हम्म, सुनना तो सुनो नहीं तो तो मुझे फायदा होता है. I whenever I see someone in front, I'm able to discuss. Otherwise, I feel कोई नहीं है. So this is energy, and suppose this is the number of electrons. Okay. And this is energy, electron energy. Okay. So at temperature for temperature T0, what you find is that the electron and a number of electrons is like this. And this energy we call EF, Fermi energy or Fermi level. So all the electrons are now, suppose we are dealing with a scenario where all the energy levels can have equal number of electrons. Okay, so there are equal number of energy levels available below and above the Fermi level. So energy levels are all symmetric. We are dealing with that ideal kind of material. Okay. So now below the Fermi level, all the energy levels are now occupied at 0 Kelvin. So this is for 0 Kelvin. Or zero, temperature zero. Not. So now you have increased the temperature, suppose, slightly. So T1 greater than E equal to 0, greater than 0. Okay. What is the distribution now? So it would look, would look this way. Okay. Now you go for another temperature, which is T2 greater than T1. So in that case, this would look, okay, it is symmetric on both the sides. Here and here would be symmetric. That we must keep in mind. So the electrons would be occupying, would now be some of the, so electrons have now a higher energy on an average, and some of them would therefore occupy energy states which are larger than the Fermi levels energy. Okay. So how this can be represented mathematically? So you would say that the Fermi for that the probability of occupancy of an energy state E, let us call this is E, okay, energy state E is exponential E minus EF by KT. K is Boltzmann constant. Okay. T is temperature. EF is this mathematical quantity Fermi level or Fermi energy E. Okay. So this is the probability distribution function. This is the probability distribution function. Fermi-Dirac probability distribution function. Fine. So, how does this behave? As we can see, as E increases beyond the Fermi level, if the temperature is 0 Kelvin, in that case, this will be this will correspond to a very large value tending to so if the temperature is below this thing and E is larger than EF, then this would tend to a very large value and tend to infinity, and therefore f of E probability would be 0. That's why. And when E is smaller than EF, then this would tend to 0 if for temperature being 0, and this would f of E would tend to 1. And that's why you have this distribution as a step here at 0 Kelvin. As you increase temperature, suppose now temperature has been increased to T1 here. So now for when you increase E beyond EF, this is now larger than so uh, you will have this will now be larger than 1. Okay. But it would not tend to infinity. would not tend to infinity. And therefore, you have a small value here. It is large because it's an exponential function. As you go slightly above kt, you will find, and kt is now small. It is larger than 0, but it is a small value. So therefore, as you know, now go slightly above kt, e minus ef, when it becomes slightly larger than kt, this rapidly falls to near 0, this f of e. Okay, but f of e nevertheless now has a value, non-zero value, for energies larger than ef. Ef is a mathematical quantity. Okay. So now, so what we find is, therefore, we find this kind of a tail here. What about the energy values here? Here you would find that as E minus EF is smaller than E is smaller than EF, then this is a negative quantity, and therefore this is smaller than 1. E to the power this thing is now smaller than 1. If it is smaller than 1, then obviously f of E is smaller than 1, but it is not very small. So that's therefore you have, so this is 1. This is some normalized value, suppose. Or you can say number of electrons divided by here n cap can be the largest number that can be occupied. Or you can also say that this is probability of occupancy. Probability of occupancy of each of the states. So it is not number of electrons, it is actually number of electrons divided by the maximum number possible for that energy state. Okay? So that is like probability of occupancy of that energy state. So here, and that probability distribution function is f of e, and it's given by this. So as we had seen at temperature 0, for any energy value larger than EF, this is 0, tends to 0, and for any energy smaller than 0, this tends to 1. Okay, so all the energy states are occupied for an energy E which is smaller than EF. Now, for as you increase temperature, we see that for E larger than EF, though this exponential factor term is very large, never, but it is not. It has a finite value. Therefore, f of E is now very small, but it is not 0. It doesn't tend to 0. Okay. Likewise, for energy smaller than EF, this is a negative value, and therefore it is smaller than 1, but still it is this f of e is now therefore, but f of e is smaller than 1 then in that case. Suppose this is 0.5, then f of e is 2 by 3. Likewise. Okay. So, right. So now let us so now you increase temperature from T1 to T2. What happens? For the same value of E, now temperature T has increased from T1 to T2. For the same value of E, now this exponential term is smaller. So f of E is larger. Therefore, for the same energy, larger probability of occupancy is there above EF. Below EF, for the same energy, KT is now larger. So it is a smaller negative value here. And therefore, the exponential exponent of E minus EF by KT is now larger. And therefore, the value of f of E is also larger. So is smaller. So that's how you find that this f of E is now smaller here, isn't? So for the same value of energy E, okay, below EF. So that is what we would be observing. So now let us Let us see what happens when for the same value of delta E, let us say delta E let us say this. You know? So f of E is 1 by 1 plus exponential delta E by kt. And now likewise, let us say that delta E2 is E f minus E2. Say that this is E1 and equally away from EF is E2. Okay. So now let us say that delta E1 is equal to delta E2. But first let us write down the probability distribution function f of E2. What is that? 1 by 1 plus exponential minus delta E2 by kt. This is the probability distribution function now, isn't? If delta E1 is equal to delta E2, then what is the relationship between f of E1 and f of E2? Let us find out. Let us see what is the value of 1 minus f of E2. So that is e to the power minus delta E2 by kt divided by 1 plus e to the power minus delta E2 by kt. What is that? That is 1 by 1 plus e to the power delta E2 by kt. Okay. So this is what it is. So what does this mean? Since we have if uh, this we were looking at, isn't? If delta E1 equal to delta E2, in that case, f of E1 is equal to minus 1 minus f of E2. So this symmetricity, something happened. So this symmetricity is the property of Fermi-Dirac distribution. So you can see that f of E1 and f of 1 minus f of E2 would be equal in case delta E1 and delta E2 are equal. Okay. So that is in case the distance from EF is equal on both the sides. So anything to discuss here? Let me manage the figures and then I'll again come back. गड़बड़ी है सब तो। हैंग हो जाता है। bar. So I don't know why it happens that way. It becomes hot and it gets. So I'll
Sir,
have to again share, isn't? I'll have to again share.
yes, sir, yes, sir. Just now it is slides are
Yeah,
not.
yeah, yeah, yeah. I'll again share. Ah, yeah. So now let us look at the semiconductor scenario. Let us again look at this n by n cap, which is the probability distribution, probability density. And let us look at this energy axis. So we said, let us say that this is the value of Fermi level EF. Yeah. So in semiconductor, as there was a discussion in the morning, so there will be an energy, valence energy, and conduction energy band. Okay, and this is the energy gap. Okay, so let us draw it better. Let us say that it is so close. Now you again superimpose this plot there. Okay, at 0 Kelvin, it would look like this. At 0 Kelvin. What does it mean? Now, whatever you have in this energy gap, in this energy gap is not of any value, isn't? So there you cannot have any occupancy. Although electron occupancy is there at the beyond this energy gap. So therefore, below this, within the valence band, below EV, all the energy states are occupied, and above above EC, all the energy states are empty at 0 Kelvin. That's what you mean to say. So now, so at 0 Kelvin, there is no occupancy anyway in the energy gap because there are no electrons in the energy gap. It's not because of the Fermi direct distribution. There are no energy states available in the energy gap. Okay. No energy states in the gap EV to EF, EV to EC. EV to EC, ideally, there are no energy states. And therefore, the occupancy is zero. Occupancy is not zero because of the Fermi direct distribution. Occupancy from EV to EC is zero because there are no energy states there. In all other energy states, the occupancy is same as that in this plot. So it's as if you have put this EC and EV here. EC and EV here. Superimposed EC superimposed EV and EC here. It's as if you have done this. Is that fine? So now again for the same value T1, for the same value T1, which is larger than 0, you will have a similar distribution as earlier. And the symmetric one here. Okay. And for T2, which is larger than T1, you will have a similar distribution as earlier. The similar here. Okay. So what is happening here? So you have in the now in the valence band, in the valence band, as you are increasing temperature, because of the more available thermal energy, electron states are getting empty. Some, is it? Likewise, in the conduction band, here, the electron states are being occupied, energy states are being occupied close to the conduction band edge. This is the conduction band edge. Okay. And close to the valence band edge, electron states are getting empty because these at the edge, the electrons are having maximum energy. They have the maximum probability to gain thermal energy and go into the conduction band. Okay. So is this fine? Now let us look at a scenario where is this Fermi level? So in silicon, this Fermi level EF is approximately close to EC plus EV by 2. Approximately. It's not exactly. But for all our calculation, for all our purposes, where we are usually teaching undergraduate courses, it is good enough to assume that it is for silicon, it is EC plus EV by 2. Okay. And energy band gap for silicon is around 1.1 electron volt. And so what is this electron volt? So if you have a 1 volt potential difference and you freely drop an electron within that, so what is the kinetic energy that if it is vacuum and you drop an electron at the further at the um, lower potential point, across an ideal, say, straight line across which there is a 1 volt drop, the kinetic energy that the electron would gain when it traverses this 1 volt drop line is 1 electron volt. You can remember it that way. Or the energy that corresponds to 1 volt energy gained by an electron uh, in a 1 volt potential drop is 1 electron volt. Okay. So this is one energy band gap is nearly 1.1 electron volt. So what? So what happens if this EF minus E2 or EF minus E1 minus EF is very large compared to KT? Why are we discussing that? See, we are saying that the energy uh, this Fermi level in silicon is very close to EC plus EV by 2. Okay, and we know that so what is the value of EF minus EV? EF minus EV is nearly equal to EC minus EF is 0.55 electron volt. Okay. What is at room temperature? What is the value of KT at room temperature? 0.026 electron volt. Okay. So EC EF minus EV and EC minus EF are both much larger than KT at room temperature. Okay, these are both very large compared to KT. Now, if I want to find out the electron probability of occupancy of electrons at the edge of conduction band, that is here, that is in this plot, in this band diagram here. So you are saying that in intrinsic silicon, EF is here. Okay. So you are discussing the electron occupancy here and here. Okay. So how will you find that out? Just at the edge. One by one plus exponential EC minus EF by KT. What is this equal to? This is now EC minus EF by KT is much larger than one, much larger than. Okay. So therefore, this is a very large quantity. So this is equal to exponential minus EC minus EF by KT. Okay. Likewise, what is the uh, probability of electron occupancy somewhere here, very close to EV? That is this band diagram here at room temperature. F of EV. This is 1 by 1 plus exponential EF minus EF minus EB by KT. Now this is now now we know that uh, this is going to be very small value compared to 1. So it will be like so you know that 1 by 1 plus x, where x is very small compared to 1, is nearly 1 minus x. So likewise, this is then 1 minus exponential minus EF minus EV by kT. Okay, so what is the probability of electron energies and energy states being empty? 1 minus f of ev at electron volt at the edge of valence band. So that is exponential minus EF minus EV by KT. Okay. So, so this and this look similar, and that there they should be, because as many electrons which leave an ideal valence band and go into the conduction band, that should be the probability of an empty energy states in the valence. Okay. So what we are observing is this is Maxwell-Boltzmann distribution. This is Fermi-Dirac distribution. This is Fermi-Dirac distribution, and this looks like Maxwell-Boltzmann distribution. So for whenever E minus EF is very large compared to KT, Maxwell Fermi-Dirac distribution reduces to Maxwell-Boltzmann distribution. What is the reason? Physically, the reason is that, as we had discussed earlier, whenever EC minus EF is very large, the almost all energy states in the conduction band are empty. Since they are all empty, it would so happen that Pauli's exclusion principle has little impact. Yeah, I'll give a 5-minute break here and then we can resume. Is that okay? Menaka, shall I give a 5-minute break?
Yes, sir. You can take the break for 5 minutes.
Yeah, yeah.
Yeah, yes,
I
sir.
think we have done for around 1 hour now, na? So that's why I was thinking that we should be giving 5 minutes break, है ना? Around
Yes.
I think 50 minutes ऐसे हुआ है ना अभी?
Yes, sir.
अच्छा, the things that I am discussing now, were they covered or नहीं?
No, sir. These were not covered.
So then
These,
it's okay, isn't it?
yes, sir.
Okay to
Yes.
cover this. Yeah,
Yes.
fine. Fine.
Yes. Okay, sir.
Huh? Any doubts? Anything you want to discuss now? After that, I can give the break.
So if any query is there, please type in the chat box regarding whatever we have covered in this last 1 hour. So I think there is no doubt regarding to this. So,
Okay.
yes, sir.
Fine. Fine.
Okay, sir.
I'll give a 5 minutes break.
Okay, sir.
हाँ हाँ रिजॉइन करता हूँ है ना. Yeah. So am I sharing the slide, sharing the screen?
Yes, sir, it is visible.
Yes. Yeah. Yeah. So let us again restart. So uh, uh, thank you. Now let us see uh, one very important property. So invariance of Fermi level in equilibrium. So let us rename the thing. Let us call it. Aha. Suppose there are two materials. Okay, some M1, M2, two arbitrary materials. Okay, and with this as the interface. And suppose both the materials are uh, close to each other. I mean, they're placed close to each other, and there any kind of material, and they are both. The entire system is in thermal equilibrium. The entire system is in thermal equilibrium. What do you mean by thermal equilibrium? So, if it is in thermal equilibrium, there is no net exchange of energy from outside the system, and also there is no net exchange of energy within the system. So, what does it mean? It means that net electrons would not be moving from one side to another. Okay, or net electrons cannot be moving from, say, a higher energy state to lower energy state. Because if electrons are moving like this, then you would be energy would be getting dissipated, or net and if electrons are moving upward in energy state, then energy would be consumed. So both cannot be happening in thermal equilibrium. So it means that the electrons, net number of electrons are not moving upward or downward the energy states. Okay, so they must be balanced. Likewise, within an electron, within an electron, within within the same energy state, if an electron moves from here till here, and net electrons are suppose moving, they are keeping on moving. So that means there must be some energy which you have to supply for them to move in one direction, keeping on moving, because otherwise there will be random movement. And then that must be balanced again by electrons moving in this direction. Okay. So, so there cannot be any exchange of net now exchange of electron energy from one higher energy state to lower energy state. Neither can be a net movement of electrons from one within the same energy state. Okay. So how is this possible? Let us see. Let us assume that there are two Fermi levels here. M2 has a Fermi level E2, M1 has a Fermi level EF1, M2 has a Fermi level EF2. If this is the scenario, then and let us say that there are two electron energy states, or there is this electron energy state E. Okay. In M2, it has um, the number of energy states is N2, and in M1, the number of energy states E is N1. Okay. So what is the probability of occupancy of N2? It is a function of E minus EF2. This is the probability of occupancy of N2. How many electrons would be moving from material 2 to material 1? That would depend on the probability of occupancy of N2 and probability of vacancy of N1, isn't within M1. So now this is f of E minus E2, probability of occupancy of N2 into f of E minus 1 minus f of E minus EF 1, isn't? This is the probability of occupancy of N1 or of energy state N1 in probability of non-occupancy in M1. Okay. This is probability of occupancy in M1, in M2. So what would this signify? This would be signifying this product would signify how many electrons would move from M2 to M1. M2 to M1. Okay. Likewise, what is the probability of electron movement from M1 to M2? That is f of similar argument. Uh, this is E minus E1 into 1 minus f of, sorry, this is EF2, this is EF1. Please stop me if whenever you feel that I need to discuss again. So in thermal equilibrium, both these moments should be equal, isn't? Only then there is no net exchange of carriers, electrons. So f of E minus EF2 into 1 minus f of E minus EF1 is equal to f of E minus EF1 into 1 minus f of E minus EF2. So what does that mean? It means f of E minus EF2 is equal to f of E minus EF1. When is it possible? It is possible only if EF2 is equal to EF1. Okay. So what do you mean by this? You mean to say that the Fermi levels must be invariant in thermal equilibrium. Fermi level is invariant in thermal equilibrium. Okay. So Fermi level is invariant. So what do you, so this is a major conclusion. And but whenever you don't have thermal equilibrium, the Fermi level, the idea of Fermi level is not valid. Then there is the idea of quasi Fermi level which we use, which we'll discuss that later. Okay. So Fermi level is invariant in thermal equilibrium. So anything you want to discuss at this point? Okay. So
Please
yeah,
ask
please.
if you have any questions. Dear audience, please ask if you have any questions so far. No questions, sir.
Okay,
Please.
fine. So now so did you was this electron hole distribution in equilibrium in intrinsic silicon discussed?
No, sir. Not discuss.
Okay. So that I will discuss now. Is that fine? So I'll keep discussing whatever was not discussed so that we go ahead. Isn't?
Yes, sir.
Uh, fine. These figures, let me move them down because I'm not going to use them now. So now let us come to equilibrium carrier concentrations. So as we had discussed, that Fermi direct distribution in intrinsic silicon, it would get reduced to Maxwell Boltzmann distribution, isn't it? So so we can say that the probability of occupancy in say valence band in conduction band, the probability of occupancy would be f of EC at the conduction band edge, and that would be at we are interested at the edge because there are very few electrons in the conduction band now, and almost all of them would be at the lowest energy. So that is they will be at the edge. So that's why we are interested at the conduction band edge. So here the probability distribution function is now a Maxwell Boltzmann distribution function. So it is exponential minus EC minus EF by KT. Okay. So what is the concentration of what is the uh, value of electrons in the conduction band? Okay, so now that would depend on how many empty energy states are there. So this is the probability of occupancy, isn't? So if you know how many empty energy states are there, so now they are numerous. So they would be of the order of 10 to the power 20 or something. Also, it will be very large per centimeter cube. It's a very large number. So with that large number, if you know the probability of occupancy, then you can also predict how many electrons per centimeter cube would be there in the conduction. Isn't? So if the number of energy states in the conduction band is say Nc, in that case, you would find that the electron concentration in intrinsic silicon and not is Nc exponential Ec minus Ef by Kt. Okay. What is this value of Nc? Nc is 2 to 2 pi So what is this Mn star? It is Mn star is the effective mass of electrons. Effective mass of electrons. What is effective mass? in this quantum, uh, uh, if you when you look at the quantum real, if the electron gains some energy, see in the conventional classical physics, what you will see, if an electron gains energy, it can move with that new energy, and it can take any value of energy. It can gain any value of energy, continuous. Whereas in quantum realm, you'll find that the electron cannot take any value of energy. It would take energies only wherever there are available states, available energy states. And it cannot take any momentum, value of momentum. Okay, so momentum and energy would be it can take values of momentum and energy according to certain principles. Okay, so it's not, so therefore, um, so those principles determine the movement of the electron. So the mass of electron would be dependent on the um, energy states available and corresponding momentum values. Okay, so this would depend on the available energy states and momentum or k states. This would determine Mn star, the effective mass. Because all the energy and momentum state cannot be uh, availed continuously. Continuous values of momentum and energy states cannot be availed. So there are some constraints, and those constraints would come out as effective mass. So the mass is determined now by the EK, energy momentum distribution, allowed energy momentum values. Okay, so that's why um, there is an effective mass, and this is Planck's constant. Planck's constant. K is Boltzmann constant. Okay, so this is derived based on the silicon. In silicon, um, what is the energy states available per centimeter cube per say per electron volt. So per centimeter cube per electron volts for every value of energy E, what is the number of energy states available? So that is integrated for all the energies above EC, and that gives this value. Okay, that we are not doing, but I have told the approach. So all the energy states above E for E greater than EC are integrated with respect to DE or added. So that gives this expression. So this NC into this is the value of N naught. Electron energy, electron number of electron concentration at in equilibrium. Okay, now it is temperature dependent. It should be. If you increase the temperature, then in the conduction band, so this is conduction band and electrons. Okay, so if you increase the temperature, the conduction band would have more electrons because now the electrons have a larger, um, a larger uh, random energy, isn't it? Or thermal energy. Okay, so now let us look at the valence band. So let us look at the edge of the valence band. Why the edge of the valence band? Because that is where the electron or non-occupancy of electron energy states would be maximum. So that is exponential minus EF minus EV by KT. Okay. Now, suppose number of electron states in this is actually 1 minus this thing. Probability of non-occupancy. This is probability of non-occupancy. At the probability of non-occupancy of valence band energy states at the edge of valence band. Okay. So now number of energy states in valence band, again it is obtained similar to NC. So it is called NV, and it is 2 times 2 pi MP star, which is the effective mass of holes KT by 3 by 2. So where are we here? So what is the probability of non-occupancy of valence bands in energy states? That probability is the probability of occupancy by holes. I think you were introduced to the idea of holes, isn't it? Electrons and holes.
Yes, sir. Yes, sir.
Yeah. So that is the probability of occupancy of holes. So what is so therefore it is this is actually hole concentration would then be given by NB, which is the number of valence band electrons energy states available into probability of their non-occupancy, which is 1 minus F of EV, which is NV exponential minus EF minus EV by KT. Okay, so now let us also observe um, another aspect of the product of or what would happen with N naught and P naught in thermal equilibrium. Suppose you have thermal equilibrium. Then number of electrons entering conduction band from valence band and vice versa, conduction band to valence band, that rate would be equal. Otherwise, there will be a net gain or net loss of energy, which is not possible in thermal equilibrium. So therefore, what would happen is that the electron and hole concentration would be constant, isn't? Because whatever was the electron concentration the rate at which it increases is also equal to the rate at which it reduces. So in thermal equilibrium, electron and hole concentration would therefore be constant. And what would be their relation? So in an ideal intrinsic semiconductor, you have excited some electrons into the conduction band, and that's how holes are created. So hole and electron concentration should be equal. Thermal equilibrium at a given temperature N naught is equal to P naught. Okay. And what happens to N naught and P naught as temperature increases? As temperature increases, both N naught and P naught should increase. Okay, equally. So if N naught is equal to P naught, then N naught into P naught, the product should also be equal. What is that? So N naught into P naught. This should also be constant. If N naught and P naught are constant, then N naught into P naught, the product should also be constant. So what is that? NC, NV. You can see from here. So in the product EF, the term EF cancels out and it is exponential minus EC minus EB by KT. What is that? NC, NV exponential minus EG by KT. And since NC and N naught and P naught are equal, we call it Ni square. So where N naught equal to P naught equal to Ni, intrinsic carrier concentration. Concentration. Okay. So now we have that. So what is the value of Ni, intrinsic carrier concentration, equal to N naught equal to P naught. So that is root NC NV exponential minus Eg by 2 kT. So what we can now um, look at what is the concentration of carrier, intrinsic carrier concentration? How does it vary with temperature? So with temperature, how does it vary? So if we plot log of this, we will see that log of Ni is equal to log of Nc Nv minus Eg by 2 kT. So this is a linear relationship with 1 by kT. Okay. So that's why if you plot it this way, if you plot by, by T. It's in other words, 1 by T with respect to log scale here. So it is suppose 10 to the power 8, 10 to the power 10, 10 to the power 12, like that. Then for silicon, 10 to the power 14, for silicon, you would observe that this would be a straight line which is coming like this. Not able to draw it properly. It is what has happened. It would be a straight line, isn't? Where does it go? Okay. So, and why should it be a straight line? That we have just now discussed. Okay. So this is about intrinsic silicon. We can discuss extrinsic silicon and carrier transport tomorrow. Is that fine? Menaka, now we should be closing, isn't? Dr.
Yes, sir.
Menaka?
Yes, sir.
Yeah.
It's already 7:10. Audience are also tired.
Yeah, yeah, yeah.
So, if you have any queries, you may ask. Otherwise, let us stop for the day. If you have any queries, please type in the chat box. Am I audible? Type Y in the chat box if I'm audible to all of you. Uh, there is no query as such, sir. So
Oh, fine. Fine. So
let
we
us.
can meet tomorrow at 10, isn't?
Yes, sir.
Okay,
So
fine, fine. Thank you.
fine. So thank you so much, sir, for
Thank
enlightening lecture, and it was really good. I hope the audience would will get benefited out of this very tough subject, a very tough topic, must I say. So I
no,
hope
no.
they will get benefited out of it. Thank you,
Yeah,
sir.
thank you. Thank you for this. Okay,
Yes.
fine.
So thank you, everyone. Let us meet tomorrow at 9 a.m. First, I'll have a lecture. After that, we have 2 hours by Professor Anand Bulusu.
Yeah.
So let's finish it for today. Thank you, sir.
Okay, thank you. Thank you, Dr. Menaka.